So now let's talk about at least one. So we still have multiple events. We have multiple people that we're selecting, multiple subjects, multiple individuals, right? More than one. But now it's going to ask you to find the probability of at least one of something happening. So first thing we got to think about. Let's give some space and talk about this. So first off, what does at least one mean? At least one is the same as one or more, right? So it's the probability of one or more. So let's think about this. So let's do a silly example. So we're going to say this is example 0 just for the sake of continuity. All right, so example 0. So if a couple wants 5 children, what's the probability that at least one is a girl? So if a couple wants to have 5 children, what's the probability that at least one of them is a girl? Well, we can definitely write all of them out, right? So one of them's a girl. So that means the first one's a girl and the rest are boys. The second one's a girl and the rest are boys. The third one's a girl and the rest are boys. The fourth one's a girl and the rest are boys. The fifth one's a girl and the rest are boys. But remember, at least one means one or more, so there could be 2 girls. So we have the first 2 are girls and the rest are boys. We could have the first one and the third one are girls and the rest are boys. The first one and the fourth one, the first one and the last one. But then we got to talk about the second one and the third one, right? And do you see that this is going to be a really long process, right? This is going to be terrible and long and gross, right? So instead, let's think about this. What would be the only case that you would not have at least one girl? So it wouldn't be all girls, right? Because that's at least one girl. It wouldn't be having 4 girls, because again, that's at least one girl. So what's the only case that we would not have at least one girl? Well, if there's no girls, right? So all of them are boys. So there's a lot of options if we're going to count all of them, if they actually are girls, but there's only one case, or if there's at least one girl, there's only one case where there's no girls. Can we see that? So would you rather have to count up all the different ways of getting at least one girl, or just finding the probability of getting no girls? Probably just this one case would be a lot easier to figure out, right? And we'll talk about how to do that because we've already talked about it really. But that leads us to the next thing. So the complement, what does complement mean again? Remember, it means opposite, right? So the complement of getting at least one would be getting what? So we said, if it's not getting at least one girl, how many girls would you be getting? No girls, right? So the opposite, the complement, is none of them. So remember, what we can end up doing is we find this probability, right? The probability of no girls. What we could do is just subtract it from 1. That's our complement, and then we'd be done. Right? This is the one case we don't want. All the other cases we do want. So if we take out this one case from 100%, we're good to go. So here's the strategy. There are 3 things that we need to remember. Oh, we can take that out. All right, 4 things. And these 4 things are the 4 steps. If you follow these 4 steps every single time, you will get at least 1 problems. Easy, down. So you just need to remember these 4 steps, and it's the exact same steps every single time. So L. So first we need to determine what L is. L is just at least one of however many subjects. So if it says that you're picking 2 people, it's at least one of 2 people. If you're saying you're picking 5 tires, at least one of 5 tires, right? That's going to be important, having this number. But remember, this is only for the at least 1 problems. So if it says at least 1, L is at least 1. LC, remember this C means complement. So what's the complement of at least 1? What did we just say? So it would be none of that many subjects. So then what we want to do is find that probability of the complement. So find the probability of the complement, which is going to be the probability of none of the subjects. So also here, saying none of something might be hard. So instead, you may have to switch it to say all of the other subjects. So for step 2, a hint might be good to just, instead of saying none of something, you say all of the other something. So for instance, if we go back to here, right? No girls meant all boys, right? If we had no girls, then that's the same thing as saying all boys. So it might be easier just to figure that out. All right, so then we want to find the probability of what we just found in step 2. And this will be using our multiple trials, right? The thing that we talked about in the last video. So we're going to be using multiple trials for this one. So we should ask ourselves, where's the and, or tell yourself the story, right? And then the last thing, what we want to find is the probability of L, which was the whole point, right? L was at least 1. We want to find the probability of at least 1. That's just going to be 1 minus the number we find in step 3. And like I said, if you know these 4 steps, this is all you need to know for the test, or for any of these at least 1 problems. All right, so example 5. If 3 families are expecting babies, find the probability that at least 1 is a baby girl. So step 1, L. L, we said, was at least 1 of how many girls? Oh, sorry, at least 1 girl of 3 families, right? At least 1 of 3 being girls. Number 2, LC. That means no girls of 3. So if none of them are girls, what are all of them going to be? All boys of 3. So find the probability of LC, right? Which is the probability of all 3 boys. And so this is why it's important to know, to have that of 3 right here, right? Because if you don't know how many boys you're looking at, you're not going to be able to do this part of the problem. So we have all boys, right? That's more than 1. So we got to tell ourselves that story. So what happens? A family has a baby and it's a boy. A family has another baby and it's a boy. A family has another baby and it's a boy. Now, some people might be confused right now. They're saying, wait a minute, I thought the whole point was to find baby girls, right? Why all of a sudden are we finding baby boys instead? Well, remember, we're trying to find the complement, right? We're trying to find this example of that one time where we have all boys, and we can take that out, so the rest we will have at least 1 girl. So if you multiply it out, what's the probability of having a baby boy? 1/2. What's the probability of having a baby boy? 1/2 and 1/2. So we end up with 1/8 or 0.125. And then for the 4th one, right, now we just need to find the probability of our event that we wanted, of L, which was just 1 minus the probability of the complement. So 1 minus 0.125, which is 0.975. And that's our final answer. Oh, sorry, 0.875. My bad. Now again, just to show you that we can do this, right? So kind of showing you what we were doing, we can actually list this out because 3 isn't bad. So for 3 babies, right? Remember we have boy, 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 girl, 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 boy, 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 girl, boy. So you can have one girl where it's first, second, or third. And then one boy where he's first, second, or third. All right? These are the only ways to get all of the 3 kids. So if you count up all the ways to have at least one girl, we can see that it's 1, 2, 3, 4, 5, 6, 7. So it's 7 out of 8, which is 0.875. But again, there's a lot of ways to do this, right? There's a lot of ways to get at least one girl. And when we had 5 girls earlier, right, that's probably way too many to count. So instead what we can do is we can say, well, there's this one case where we don't have any girls, right? And that's just 1 out of 8. So if we subtract that from 1, right, that means that the other 7 have to be at least one girl, which is 0.875. So essentially this is what we ended up doing, right? We found the probability of none of them being girls, and then we just subtracted that from 1. And again, the reason why is because when this number gets really big, if you have 5, 6, 7, 8 kids, it's going to be way too much to just write it all out. So instead, we take the one case and subtract it from 100%. But we end up with the same answer both times. All right, let's do another one. So Topford supplies X data DVDs in lots of 50, and they have reported defective rate of 0.5%. What's the probability of getting at least one defective disk in a lot of 4? And let's assume that the events are independent. All right, so it says at least one, so we're going to do our steps. Step 1, L. L is at least one defective of a lot of 4. Number 2, LC. So none defective of 4. All right, number 3. So now we got to find the probability of the complement, right? So if none of the 4 are defective, what do you know about all of them? All 4 are what? All 4 are good. Good. So that means we have a good one, and a good one, and a good one, and a good one, right? All 4 are good. So we can just rewrite as probability of good, probability of good, probability of good, probability of good. And remember, the reason why we're doing it is because we want none of them defective. If you take out that one case, then the rest of them are going to be at least one defective. All right? So what is the probability that one of them is good? Well, if the defective rate is 0.5%, right? Then what's the good rate, right? What's the probability that it's going to be a good disk? So if you can only have defective or good disks, you can just subtract it from 100%, right? 100% minus 0.5% is 99.5%. So the probability of a good disk is 99.5%. So we see that, oh, I guess we can just write over here. So 0.995 times, since they're independent, it's 0.995, 0.995, and 0.995. And we multiply those numbers out. We should get about 0.9801495-ish. So part 4, last step, We just have to subtract that from 1, right? Because that's the one case that we don't want. So 0.980149.5, if we subtract that from 1, we get 0.01, nope, we round correctly, 0.020. All right. Would this be considered unusual? Yeah, this would be unusual. Because it's less than 0.05. Good. Let's do another one. So a bag contains 14 blue M&Ms, 6 yellow M&Ms, and 8 green M&Ms. If you randomly picked and ate 4 M&Ms, what is the probability that at least one of them were blue? So at least one. So we do our 4 steps. Step 1, L. At least one blue of 4 M&Ms. Step 2, LC. So the complement of at least one blue is none blue of 4. So probability of the complement. So if they're not blue, then they're either going to be yellow or green, right? Some other color. And it doesn't matter which one, right? We don't care if it's yellow or green. They can be any combination of the two. So basically, we want not blue. The first one we pick out is not blue. And the second one is not blue. And the third one is not blue. And the fourth one is not blue. All right. So, what is the probability of not getting a blue one? Well, we can see that you would either be getting a yellow M&M or a green M&M. How many of those are there? We can see that if we add those together, we would be getting 14 out of, if we add them all together, 28. So there are 14 M&Ms that are not blue out of a total of 28. All right. What about the second one? Well, notice, right, we ate that M&M. Again, we don't know if we ate a yellow M&M or a green M&M, but we just know we didn't eat a blue one. So there's one less M&M because you ate it, but then there's one less M&M that's not blue, right? It's either yellow or green that we ate. So there would only be 13 M&Ms that are not blue. If we do it again, right, now you've eaten 2 M&Ms. So there's, again, one less M&M. And there's one less not blue M&M. And then again, be 11 over 25, right? There's one less M&M, one less M&M that's not blue. When you multiply these together, you should get about 0.049. Don't forget, though, that's only step 3. Step 4, we just subtract that number from 1. So we get about 1 minus 0.049 to get 0.951. So that's our final answer, 0.951. Is this unusual? No, this is very usual. Because it's very above 5%, right? It's almost certain, almost. All right. Problem number 2. So this is again in our word problems. So a tire factory is randomly selected, a tire factory that randomly selects a sample of items without replacement will accept an entire batch if at least one item is okay. In one day, the factory manufactured 2134 tires and 468 of them were good. So if tires are randomly selected for testing, what's the probability that the entire batch will be accepted? So again, you just got to read. We want the probability that the entire batch will be accepted. So when will the entire batch be accepted? It says we will accept the entire batch if at least one item is okay. So we have at least one. So step 1, L. At least one okay of how many tires? So how many are we selecting? So 5 tires are selected. So a 5. Number 2, LC, the complement. So at least one is okay. The opposite would be that none are okay of 5. So what would that mean? All of them are defective. Or we can say bad if that makes it easier. Just less words to write. So all 5 are bad. All right. So now we got to find the probability of LC. So the probability that all 5 are bad. So that's more than one. So tell yourself the story. That means the first one was bad, the second one was bad, the third one was bad, and the fourth one was bad, and the fifth one was bad. And there you see where our ands are, right? The first one's bad, and the second one's bad, and the third one probably should be a B instead of a 5. I don't know why I wrote a 5. My bad. Huh. Get it? Bad. My bad. Anyway. All right. So what's the probability that the first one's bad? So if we have a total of 2134 tires and 468 of them are good, then how many are bad? Well, UBC, we can just subtract, right? 2134 minus 468. And if you do that in your calculator, you'll see it's 1,666 tires are bad. Right? So the probability of a bad is all of the bad ones divided by the total. So 1,666 divided by the total of 2134. Then you get the second one. Now notice, right, it says it's without replacement. That's very different than if it said with replacement. So since we took a bad one out, we're keeping the bad one out. So we have one less tire. And since the first one was bad, we have one less bad tire. All right? And keep going. We have one less tire, one less bad tire. One less tire, one less bad tire. One less tire, one less bad tire. Good. And we multiply all that out, we get about 0.290. And I would actually suggest multiplying these out. Making sure that you understand how to use your calculator is always going to be very important. So if you're not getting this answer, that means you might not be doing the calculator right. So double check, pause the video, make sure that you're getting the same numbers I'm getting. If you don't understand, make sure to email me, contact me somehow. Number 4. So that was the probability of the complement. So now we need the probability of the actual event. So we just subtract it from 1. So 1 minus 0.29. And we get about 0.710. So, would that be considered unusual? Would it be unusual to accept an entire batch? This time, no, it would not. Because 0.710 is way bigger than 0.05, right? 71%, that's definitely usual. All right. So if you need more practice, I have uploaded that as well for this activity for all of the probabilities. But if you have any more questions, feel free to always contact me. Have a great day.